Okay, great. Thank you for joining the webinar today. We have quite a few people registered. This is going to be a very well-attended webinar. So just quickly introducing our speakers today. From EPA, Office of Research and Development, we have Paul Meyer and Tammy Newcomer-Johnson. From two of our research centers, ORD has 4 research centers, and they are from 2 of those centers. And then we also have Sujay Kushal with us from the University of Maryland, and Joe Galella also from the University of Maryland. And with that, I'm going to go ahead and I'm going to turn it over to Paul, who's going to start the presentation.
Hi, thanks, Michelle. Can you hear me?
Hi, Paul. Yep.
Okay, great. Well, welcome everybody. Thank you for joining us. I'm Paul Meyer. This will be a joint coast-to-coast presentation with my colleagues. And we're going to talk today about an emerging water quality threat, freshwater salinization. And just to give you an overview of the presentation, we're going to talk about our past research and sort of how it's evolved into our current examination of this issue of freshwater salinization. We're going to explain what freshwater salinization syndrome is and how it contributes to chemical cocktails. We're going to talk about national and global patterns in this phenomenon and discuss the impacts on human health and the environment. And then we're going to talk about some ways in which we've developed to monitor this phenomenon, and we're going to wrap up with a discussion about how to manage this issue and then some of our future research. Next slide, please. So our research over the past 20 years is focused on protecting water quality from pollutants like nitrogen, phosphorus, heavy metals, sediment, and more recently salt. And you might recognize this satellite photo as one of the Chesapeake Bay. And you can see in this photo, these darker brown lines, which represent sediment flowing down some of the rivers and into this bay. And this happens in Chesapeake Bay and in receiving water bodies all around the world. And the point is that streams are conduits of pollutants. Next slide, please. And pollutant transport, like this, is exacerbated by impairments of those streams. So we've looked at how in urban ecosystems, those streams can be degraded by flashy flows from impervious surfaces, leading to erosion, damaged infrastructure, hydrologic disconnection, and ultimately impaired biogeochemistry. Next slide, please. We've looked at how disconnecting streams from their floodplain impairs them. For example, when they're placed in concrete conduits, it makes it for a very efficient, effective transport of solutes and pollutants. Next slide. And we've examined streams that are buried, which is often the case in urban ecosystems to facilitate construction of roads, buildings, and so forth. Next slide. And with all of these impairments, we've looked at ways to remediate these streams, impairments in these streams, such as through stream restoration, which has become a multi-billion-dollar industry that often relies on re-engineering channels in various ways to repair the effects of urbanization. Next slide. We've looked at ways to restore streams by removing sediments from floodplains, these so-called legacy sediments, or legacy sediments that have been deposited in some cases since the beginning of colonial era development. Next slide. And we've looked at stormwater management approaches like this highly engineered approach to stormwater management, regenerative stormwater conveyance, which is sometimes employed to improve nitrogen uptake. Next slide. And altogether, we've synthesized our work in papers like the one that Tammy Newcomer-Johnson led, describing the effects of stream restoration on nitrogen removal. Next slide. collectively, these efforts have culminated into management tools, which is of course, our objective, like the recently revised protocols for restoring streams in the Chesapeake Bay to optimize management of nitrogen. So, and this is a preface to set up our talk today, because, next slide, please. So, despite all of this effort in research and developing BMPs for these impairments, recently we've discovered an insidious threat to water quality that has the potential to overwhelm existing management and restoration efforts, and that is freshwater salinization. For example, we found that road salts, in this case, contributed to peaks in conductivity and ions in a stream that we examined in Baltimore. So these are data from a paper that we published led by Curtis Cooper showing peaks in specific conductance, chloride, calcium, magnesium, and sodium along a stream that we sampled from top to bottom. We see peaks in chloride and specific conductance where the stream emerges from a stormwater outfall in downtown Baltimore. And then another significant peak where the stream crosses I-695, which is a very busy, heavily salted highway that circles the city. So this is a stream that underwent a multi-million-dollar restoration effort some years ago, the benefits of which may be swamped by the effects of freshwater salinization syndrome. So I'm going to hand it off to Dr. Newcomer Johnson to tell you what freshwater salinization is and where these salts come from, and ultimately what the impacts are.
Thank you, Paul, for setting the stage regarding restoration and challenges for watershed management. The freshwater salinization syndrome is an emerging global problem impacting safe drinking water, ecosystem health and biodiversity, infrastructure corrosion, and food production. Next, I'll be discussing some of the sources of freshwater salinization. Next slide, please. Freshwater salinization originates from diverse anthropogenic and geological sources, including road salt application. Surface water concentrations of road salt constituents such as sodium and chloride are increasing both locally and nationally. Sujay will show some of these trends later on in our presentation. Currently, road salt is not regulated in the United States, and in some areas where road salt is applied, surface water can be 25% as saline as seawater during winter. Concentrations of chloride greater than 250 milligrams per liter can be toxic to freshwater organisms and may affect ecosystem function. Next slide. The freshwater salinization syndrome is also attributed to human accelerated weathering of infrastructure, rocks, and soils. For example, highly urbanized settings often contain structures built from limestone, concrete, gypsum, and other materials which release major ions when weathered. During construction, materials from bedrock are released by weathering. Soils are exposed to erosion and weathering, and more ions are mobilized into the surrounding environment. In fact, many constructed drainage systems in urbanized areas can be rich in carbonates and other major ions. The release of these ions due to weathering contributes to distinct urban lithology, known as urban karst. Urban karst is usually more than half limestone, and with absorption over decades, it becomes calcium carbonate. Again, can you hear me? I'll turn off my video in case that's causing a problem.
Yes, I can hear you now.
Okay, fantastic. So in this next slide, we put together what I consider to be a pretty fun conceptual model to illustrate how distinct combinations of elements can be grouped as chemical cocktails and transported in urban waters. Elemental inputs to the watershed originate from different urban geochemical sources and processes. Chemical cocktails are mixed hydrologically across time and space in watersheds through surface flow paths, such as impervious surfaces, construction materials, altered geomorphology, and others, and subsurface flow paths, which can include buried streams, urban karst, pipes, and soil compaction. Urban geochemical processes form distinct elemental combinations of nutrients, metals, salt ions, and organics that are transported and transformed along hydrologic flow paths based on factors such as chemical mobility, particle size, and reactivity. These different chemical cocktails can become mixed together along hydrologic flow paths, and their sources may be traced using diverse analytical approaches. A key takeaway from this diagram is that salinization can facilitate chemical cocktail production. Next slide, please. Our research team has documented how road salts, weathering of impervious surfaces, and sewage have contributed to the freshwater salinization syndrome and the production of unique chemical cocktails with elevated levels of base cations, such as calcium, magnesium, potassium, and sodium. Next slide. Next slide, please. Can you hear me, or do you need me to call in? Okay, here it goes. Joe, who'll be presenting later in this presentation, put together this slide to demonstrate how these elevated base cations can outcompete metals at cation exchange sites on sediment particles. Calcium and magnesium are particularly efficient at mobilizing cadmium and manganese because they're divalent. And later in our presentation, Joe will be sharing some interesting data linking salinization and metals from both lab and field experiments. So now I'm going to jump up from the molecular scale back up to the watershed scale. Next slide, please. And this is where I'm located in Cincinnati, Ohio. The Mill Creek watershed here. Mill Creek has been called by American Rivers one of the most endangered urban rivers in North America, and this watershed is impaired by stream burial and chemical cocktails including chloride and nutrients from combined sewer overflows, shown in the dark circles, and road salt and industrial pollutants like PCBs and metals. The good news for the Mill Creek is that the green symbols show that over multiple decades, a variety of green infrastructure and stream restoration projects have been conducted to restore the watershed. However, there's still a lot of work to be done. Paul and I have shown some examples from the Chesapeake watershed in the Midwest, and now I'll be passing over to Sujay, who will show that these freshwater salinization trends are occurring at many other places all over the globe. And you can pass it to Sujay, please.
Thanks, Tammy. So this is a pattern that's affecting us across different areas of the United States. The fastest rates of increase are actually in North Dakota, and that's probably because of the geology in addition to the road salt, but then also up and down the East Coast where a large number of the U.S. population resides up and down the East Coast, and it impacts drinking water supplies. This is a map showing increasing trends in specific conductance with data that's over 50 years old. The up arrows indicate the increasing trends, and then the level of color indicate the rates of the trends. You also see increasing trends in pH, and these increases in ions that we see also affect many other chemical parameters like pH, solubility of metals, and mobilization of radionuclides, which I'll talk about a little bit later. So if you can move to the next slide, please. So as I mentioned before, we've seen these trends in different areas of the United States. So whether you're in Texas or in Missouri or in North Carolina, Connecticut, there are these increasing trends in specific conductance, and they're actually driven by different types of ion mixtures depending on where you're located. So it's almost like different regions of the United States are affected by these different chemical cocktails that are local, that are affected by road salts, wastewater inputs, fertilizers, and different mixtures. And so that the different chemical cocktails can have potentially different effects on ecosystems. But currently we look at one element at a time when we do management. But what we're trying to get across is that there are different mixtures and chemical cocktails which may have these effects and interactions that we don't really know about as well. So next slide. Next slide.
Slide 26 is showing right now.
Okay. So this also shows that these trends are happening on a global scale. So these are rivers and lakes across the world, and they're increasing patterns and concentrations of sodium and calcium, magnesium, potassium, and this includes some of the Laurentian Great Lakes, which are about 20% of fresh water. This is happening at a very broad scale, across the world as well, not just in the United States. Okay, next slide. Next slide. Here, I'll shut off my camera. Maybe that'll help. So the other what we did is we made a conceptual model of what's causing these changes in ion concentrations. What happens is in the beginning we thought, oh, it's just road salt, and that was what we focused on. But now we know, as Tammy mentioned, it's a wide variety of different chemical cocktails, and that actually starts with the geology of the watershed, where you have acidic precipitation that weathers different types of bedrock, and so that contributes ions. And then you have this human acceleration of the weathering or breakdown of rocks. And now we also know that there's increased human inputs coming from road salts, agricultural lime. Also, energy and resource extraction can contribute to brine formation. There are biological processes, but that also contribute to changes in ion concentrations. But basically, there's a ripple effect where in the headwaters you have these sources that accumulate and contribute to freshwater salinization syndrome, and then the net effect is that you get increasing concentrations, changes in pH, and solubility of metals that can affect drinking water contamination, mobilization of contaminants, and also potentially impact coastal zones as well. Next slide. So there are different environmental, economic, and health impacts of freshwater salinization syndrome, and that's why Paul mentioned that it's an emerging issue. So next slide. About 15 years ago, we focused mostly on chloride pollution, and so this is the Baltimore drinking water supply, and it showed almost a quadrupling within a 25-year period. And back about 15 years ago, in a paper that we published, we mentioned that this would be a drinking water quality issue within the century, affecting the potability of some potential drinking water supplies in the northeastern United States. Since that time, we've known that it's affected more than chloride ions. If you look at the bottom left, there's other ions that are affected, and then on the right-hand side, you can see that there's all these trends that are similar, not just with chloride, but with other ions like sodium, calcium, and magnesium. And I just want to point out, I don't know if there are any people on this call that are in public works or local or state agencies, but these figures that on the left and the right, they were through the collaboration with a guy named Bill Stack, who worked for the Baltimore Department of Public Works. He retired, I don't know, maybe it's been 5 or 10 years ago, but he took me under his wing, and he also worked with Tammy and Paul very closely. And so there's a huge potential for collaboration with public works and state and local agencies to kind of get at this problem. Bill noticed these trends actually in the reservoir, and he said, Sujay, what's causing these trends? And then we started figuring out that it's related to other elements and other chemicals that you see on the right-hand side. And then we learned that it actually was happening not just in Baltimore, but it was happening across Maryland, the Northeast, and then the United States, and then the globe. And Bill was actually a co-author on these papers as well. The next slide. So lots of potential for academic and local and state agency partnerships, in addition to the federal partnerships that we have with EPA, with Tammy and Paul, but on this issue. So other researchers have shown that showing that this is an emerging issue too. Recent papers are showing that there's direct effects of the salinity on toxicology, but there's also indirect effects too, where there's interactions with the salts and other ions or other stressors. So this is something that people are working on, where we're just learning more about it every day. Different studies come out. These are just some examples. Okay, next slide. One thing that's well known, but it's receiving more attention too, is that there are economic consequences of this issue. Sodium chloride can cause damage to concrete and rebar structures in concrete, and it can cause corrosion. It can affect automobiles. I don't know if anybody here is in the Northeast, but you can look at the bottom of cars. You can tell. I can tell if I'm in upstate New York, if somebody lives in upstate New York, just by their car sometimes, and some of the corrosion issues. But there's also scaling in power plants. So we rely on water from streams and rivers in power generation, and so when that water evaporates, when it's used to generate steam, it can create a scale, which can affect that scale, and that buildup can affect pipes and their ability to transport water. Also in heating systems where you have steam generation, that scale deposit can also affect that infrastructure as well. But the impacts of salt can cause potentially billions of dollars of damage in infrastructure with roads, pipes, and our cars. That's something to pay attention to, in addition to the ecological and potential health implications. Next slide. And speaking of these health implications, that's not been really researched very well. This is a table from a paper, a very extensive table put together by a student of ours, Carly Moss, who's a co-author on this paper, where we investigated the potential health risks of salinization. And so there's a lot of potential impacts that need further work and further investigation, both direct and indirect effects of the salt. So there's salt-sensitive conditions like hypertension and kidney dialysis, where people limit their sodium intake in foods, but we don't always consider water as a source of sodium as well. And during the winter months, when our sodium and chloride levels increase in some areas due to road salt or other sources, we may need to consider that as an additional salt source. The other potentially big issue is the corrosion of water infrastructure and corrosion of pipes, where you have increased chloride, which can affect the corrosivity of the water, and that corrosion can affect old pipes. Like, for example, in our neighborhood outside of Washington, D.C., there's old cast iron pipes, and so there can be interactions with the chloride-rich water, and then the release of iron and manganese and dissolution of oxides of iron and manganese, which can also release metals into the water. So you have drinking water that's tested at the water treatment plant, but that water has basically interacts with extensive pipe systems as it goes to our house, which is difficult to test and monitor every aspect of that distribution system. So the interactions with pipes and salty water is really important. Next slide. So I'm going to turn it over to Joe Galella, who's going to talk about monitoring freshwater salinization syndrome and chemical cocktails, and some of the advancements that he's making with that. Okay, so thanks, Galen.
Thank you, CJ. Next slide, please. So as Sujay just mentioned, freshwater salinization syndrome and associated chemical cocktails have been well documented on a national scale for over 50 years. To differentiate my research, I focus on a finer spatial and temporal scale. sampling local streams in Baltimore and Washington on a biweekly basis. I analyzed these for major and trace elements over multiple years, and noted that there were noticeable correlations between specific conductance as measured by the USGS and the major and trace elements that I was sampling for. So as you can see, it's a log scale on the right y-axis, so those small changes are relatively large changes in actuality, but every time there's a peak in the thin blue line without the dots, that's the specific conductance. Everything else tends to follow. And also the specific conductance readings that we were getting were relatively frightening, with them being well over the concentrations of chloride found in Gatorade as well as ramen, at least 4 times a year, just in this short sampling window. So that's the salt concentrations alone, disregarding the other elements which are mobilized, are biologically concerning. And we also found that manganese, which is a neurotoxin, was severely elevated during the winters, being over 12 times the EPA limit. So it reached up to 0.6 milligrams per liter, and the EPA limit is 0.05 milligrams per liter, where that little dotted line is. So pretty scary stuff. Next slide, please. And as I mentioned, there was a correlation between specific conductance and these major and trace elements. We found that manganese and copper had the strongest among them, and we thought about using them as a proxy. So the analysis that I conducted used an ICP OES analyzer, which is very costly to buy and as well as operate. So we thought that if we could use specific conductance, which the sensors are pretty ubiquitous, the USGS has them on thousands of streams, as well as they're very inexpensive for private use. We wanted to be able to use the power of that to kind of provide a proxy and potentially monitor for these mobilizations and a wider range than just this research. Next slide, please. So as you can see here, just using simple linear regressions and relationships, we were able to get a fairly robust prediction from just simply using specific conductance for both copper and manganese. They had good Nash-Sutcliffe efficiencies and are very promising for future use. Definitely need to collect some more data before it's we can say that this is happening everywhere. This is just on Sligo Creek in Washington, D.C., where the data was collected, but it seems to be a very promising first step. Next slide, please. So to kind of dovetail off of this research, the research that I'm currently conducting is looking at different stormwater management features around the University of Maryland campus. And I am sampling both the sediment as well as water from all these features and kind of dosing it with different varying levels of salt, and then as well as that varying different salt, so not just sodium chloride, but also calcium chloride and magnesium chloride. And you can see the 8 sites that I selected on this map on the right around campus. I'm doing duplicates of bioretention, wetland, ponds, as well as bioswales, which are also called rain gardens sometimes. So next slide, please. So I collect these samples, add a known quantity of the sediment as well as a known quantity of water to these little aliquots on this shaking table, shake them for 24 hours, and then analyze for inorganic and organic carbon as well as nitrogen on our TOC analyzer, and then major and trace elements on our ICP OES. Next slide, please. And here's some preliminary results. I'm only about a third to a halfway done with this, so definitely will be updating as time goes on. But it looks like the total nitrogen, the non-purgeable organic carbon, as well as the inorganic carbon have positive relationships with the amount of chloride added. All this is normalized to grams of chloride per liter in the solution. So as you go right on the graphs, the concentration increases, and you can see that nitrogen, inorganic carbon, and organic carbon all increase. Next slide, please. And this is even more interesting. We can see here, looking at major and trace elements with looking at metals, the different stormwater management features behave differently depending on the location. So normalized to sodium chloride, that's the salt added to all these. It looks like bioretention mobilizes the most copper, while wetlands mobilize the most manganese and strontium so far in this analysis. We still have more features to look at, and it looks like for manganese, it's more variable, but there appears to be a dip at middle concentrations, and then it elevates higher at very high concentrations. That's an interesting phenomenon to look into more. Next slide, please. And this isn't from our lab, but in 2017, the drinking water in Montgomery County turned brown due to high manganese levels, according to the Washington Suburban Sanitary Commission, and reported on by the Washington Post. Water lines had to be flushed to temporarily correct this issue. So if our monitoring is picking this up in the streams, it looks like there's also a possibility of this making its way to end users of drinking water. And I think after this, we're going back to Paul to kind of wrap everything back up.
Yes. Thanks, Joe. Can you hear me?
Yes, we can hear you.
Okay, great. Thank you. Thank you, Joe. As I said in the beginning, our mission as an agency is to protect water quality. So it's not just enough to describe the impacts of freshwater salinization or the trends and so forth. What we seek are ways to manage this emerging issue. And in a recent paper, my colleagues described multiple approaches to managing freshwater salinization syndrome, including taking a watershed ecosystem approach, monitoring multiple elements simultaneously, managing stormwater, remediating groundwater, addressing this issue of road salts, which, as we've seen, is a major contributor to freshwater salinization, understanding how drinking water supplies may be affected, and then understanding how existing regulations might be effective at addressing the situation. Next slide, please. So that paper appeared in Biogeochemistry, and I invite you to look at that paper in more detail. We don't have enough time here to go into each of those issues in great detail. That paper provides a lot more background information, and I invite you to look at that paper. So what I will do is talk about some work that we've done to look at specific issues, and I'll cover a few avenues of management that we've been examining. So one of those issues, of course, is road salt, and there's been a lot of effort devoted by researchers and transportation agencies to reduce the impact of road salt. You know, we can't stop using road salt if we're going to drive in the winter on icy roads. It's critical for safety, but we can strive to limit application of road salt. And one way to do that is to apply salt by brines instead of by applying it in solid form. And oftentimes by doing that, you end up with these large deposits that are, you know, commonly seen in the winter. Others have looked at salt substitutes, even things like industrial byproducts like beet juice that show promise as a de-icer. And there are various approaches to timing and dosing in coordination with weather conditions. But we know that salt from roads and other sources are entering our streams. It's there already, and the question is what to do when the salts are already released into the environment. Next slide, please. So we know from our work that it is extremely important to capture that first flush of salts coming from roads and impervious surfaces. These data are from a paper we published a few years ago. They show that the peak in specific conductance, shown here in red, which is in this case driven by chloride from road salts, actually appears before the hydrograph shows the peak in stream discharge, shown in blue, even during a rather small precipitation event. So this just demonstrates that it's important to capture that flush of salts that come from roads and impervious surfaces, because once it's off of the road and into the stream, it's much more difficult to manage. Next slide, please. So we know too that geomorphology dictates the behavior of salts moving through streams and the surrounding groundwater. These data show the difference in chloride concentration in the surface water of a stream. You can see the line in blue shows the chloride concentration over time. And in comparison, the chloride concentration in groundwater in various stream features of that stream, including the hyporheic zone, riffle pool zones, cut banks, and terrace features. And this variation in concentration is a function of how water moves through the ground and how it carries solutes to those zones. And the point here is that we can potentially take advantage of this phenomenon. Next slide, please. So we can take advantage of this phenomenon as demonstrated in a paper published by Carly Moss, current student in the Kaushal lab. Carly showed that stormwater features and the associated accidental wetlands, in this case, an accidental wetland is a feature that forms within the stormwater structure itself. These features can actually reduce peak salinities by 94% and attenuate salt pulses by up to 45 days. Because these systems retain groundwater like a sponge, and they retain the solutes in that groundwater and slowly release them over time, so you don't have this very big peak, this slug of salt that can enter into local streams. Next slide. Other researchers have shown the same phenomenon, the same behavior in bioswales and in impervious pavements, where runoff is collected into retention features and then the solutes are released slowly and those peaks are reduced. Next slide. So from Carly's results and others, it's very clear how important it is to understand groundwater surface water interaction, and how these salts and where these salts are retained in the system, so that we can better manipulate BMPs for salt management. For example, this figure shows specific conductance peaks in a stream during a rather large rainfall. And it shows that specific conductance peaks very quickly in the surface water after that rain event. This was a big storm, flushed a lot of chloride and salts, reflected in the very high conductivity levels equivalent to about 8,000 milligrams chloride per liter. That peak declines very quickly as well, dropping even lower than before, kind of giving that false assurance that chloride has left the system, but actually chloride is hiding in the groundwater, both in the hyporheic zone, which is shown in the green line, where specific conductance remained elevated for 2 days, and then also in the banks of the stream, represented in the black and red lines, where specific conductance was elevated for several days. So it's important to understand these behaviors and important to understand this relationship between peaks in conductivity and, of course, associated elements that are dissolved in those flows, and to understand how we can apply best management practices and which best management practices might be best for attenuating this salt pulse. Next slide. So as we've seen, this issue of salt entering into streams it's a very difficult phenomenon to monitor. Assessing the impact of freshwater salinization syndrome is difficult because you have these peaks and fluctuations in salts that are flashy, very ephemeral. So capturing the behavior of those salts and associated chemical cocktails of concern is difficult using standard grab sample techniques. So in this conceptual figure, we can imagine 3 elements of concern that vary widely over time, and identifying episodes where water quality may be particularly impaired would be difficult, as you might imagine. But as Joe's research shows, we can potentially employ sensors to monitor specific conductance in real time as proxies that reflect the likelihood that we have high chemical cocktail loads in the system, and thereby use this approach of sensors as an early warning system where we could identify those periods of time when utilities might be made aware of the situation and be better prepared for it, and be able to better manage it or treat drinking water supplies, for example. Next slide, please. So I'm going to wrap it up here with a couple more slides, summary slides. We can see clearly from these issues that we have a number of challenges for the future, including protecting drinking water supplies, understanding whether there are effective salt reduction methods and alternatives to salts, and how to remediate that salt once it's in the environment and how to manage it. We know that it's difficult to monitor these flashy phenomenon, and it's imperative that we understand how to manage these suite of chemical cocktails. Next slide, please. But we know already that based on our research and others, that freshwater salinization syndrome is an emerging threat to water quality. You know that there are multiple sources of salt that create chemical cocktails. We know that these salts and the associated elements mobilized by those salts are highly variable in time and space. We suggest that monitoring of these elements could be improved by the use of sensors, and we also argue that management must be multi-pronged and holistic to address this very complicated and multifaceted issue. So with that, I'll thank you all for listening.
And again, I want to thank our presenters and thank you all for joining us today.
Thanks to everybody.